Okay, guys. Hi, I'm Duncan, and I'm a Senior Solutions Architect at Kyvos Insights. And today I'm going to be talking about how Kyvos enables analytics at speeds hundreds of times faster than complementary solutions, even at data sets and scales that are much larger than you might initially expect. And as a part of this, I'm going to be covering a lot of ground today, and I don't have a whole lot of time to do it with. So I just ask that you hold any comments and questions until after the presentation. So today we're going to be talking about the problem that Kyvos solves. Okay, so why do we exist? We'll talk a little bit about what we do, and then we'll talk about why we think our technology is really better than legacy alternatives. And then we'll end the presentation just by giving you a quick preview of how Kyvos works. That being said, let's get started. So Kyvos exists because of what we call the cloud analytics performance gap. And that gap occurs because in the cloud, you're literally renting resources by the second. And so as such, long processes actually cost you more than shorter ones. So in the cloud, time really is money because you're running those resources. And that means that slow queries actually cost you more than expensive ones. And as such, query performance is really no longer a luxury. It's an absolute necessity. And if your query performance SLA really isn't desired to be sub-second, you're literally just wasting money at the end of every month. Well, the good news is Kyvos is a purpose-built analytics acceleration platform. And we're specifically designed to enable sub-second queries, even with thousands of users, and that query performance does not significantly degrade with query concurrency, working against hundreds of millions, billions, or even trillions of rows. We work with all major cloud providers, as well as some of the minor ones, because at the end of the day, we're really just Linux under the hood. Okay, so we talked a little bit about the challenge that we're trying to solve. We'll talk a little bit about what we are. So Kyvos is a universal semantic layer. And our flavor of semantic layer really focuses on two major things. One, the organization of data, as well as the acceleration of it. So, as a semantic layer, we provide a single version of the truth, and we try to standardize metrics so that there's no debate about a given definition. But one of the coolest things about Kyvos is that we're not a relational database on the back end. So we can natively organize your schema into a series of nested folders. And the idea related to that is that it's a self-explanatory schema. So really, regardless of your level of familiarity with the underlying data set, you can immediately identify the right data to analyze. And in Kyvos, you pre-curate your schema before you actually deploy it. And as a part of this, we can say with 100% accuracy that all of your answers that you get from Kyvos will always be 100% accurate because we have no query time joins. And as such, that really breaks down the barriers to analytics consumption that have historically challenged the industry, really meaning that anyone, regardless of technical ability, can answer any question at any data scale. And then on top of that, we provide a best of both worlds implementation of both raw and aggregated data. So you can leverage aggregates for trend analyses and row-level data for audit purposes. Now, data mesh architectures have become extremely popular lately, and Kyvos really helps to simplify their consumption and accelerate their content. So whether you're an individual department or data domain publishing an individual data product, or if you're trying to mesh together multiple data products into a single cohesive whole, in Kyvos, you're always going to be consuming a single object. So as such, we not only accelerate it, we actually enable that consumption to be much easier because your end users don't need to know anything about the underlying data structure. And one of the things that we help out a lot with are MOLAP cube modernization. And the reason why this is important is there are a lot of departments and companies that really love MOLAP technology or multidimensional OLAP. And as a part of that, they've been holding on to the technology for a long time because really nothing before Kyvos has provided that same level of interactivity with your data, where you can instantly pivot your analyses in any directions as you follow a trail of analytic breadcrumbs down to your underlying root cause. Now, Kyvos preserves that kind of snappy performance, but adds infinite scalability to that analysis. The other thing that Kyvos adds on top of traditional MOLAP technology is one, the ability to work with real-time data instead of just historical data, and two, the ability to deploy predictive content as well. And with Kyvos, your data is always available for query, unlike traditional MOLAP. And we're actually disk-based, and so we're not RAM-bound. And that means we can scale really frictionlessly to higher levels. And we have an intelligent cache that not only accelerates known queries like reports and dashboards, but also unknown queries for ad hoc purposes, because the cache actually operates on query patterns which involve columns that you sort and group data by instead of just a traditional historical query result set replay. And if you've spent a lot of time developing a lot of content on a legacy MOLAP solution, our automated migration tool will enable you to quickly and easily convert your schema into a Kyvos model, which will make it cloud ready. On the data science side, we provide an ultra high performance feature store that's particularly conducive to exploratory data analysis. So if you have to work with hundreds, if not thousands of candidate features, Kyvos' extreme query performance and scalability make that process a process that can be measured in days to weeks instead of months or weeks to months like alternative platforms. And then on top of that, Kyvos is a semantic layer. And the reason why that's important with regards to data science is that a data science project would actually combine the skill sets of multiple domains. So you might have a domain expert, you might have a data expert, you might have an application developer, and then of course the data scientist as well. And each one of those skill sets brings a favorite query tool and query language to the table. And the good news is Kyvos speaks all of them. But beyond that, we can really facilitate collaboration as you examine features even further, because we have a no-code way to explore our data, which will help your team to quickly move in a directionally correct manner as you identify your final feature set that you want to use to train your algorithms with. And then at the end of the day, Kyvos is a data store. So you can deploy predictions directly into the semantic layer itself so that they can be consumed by either human users or applications. Now, one of the other ways that Kyvos changes the paradigm of a semantic layer is that we incorporated real-time streaming data. So what that means is it's only seconds between the appearance of data on the source system and when a visualized output from your analysis is available, thanks to Kyvos. And another really cool thing about Kyvos' version of real-time is, in opposed to really the rest of the analytics industry, whereby streaming and real-time data really requires very technical resources to enable, we actually have a zero-code connection to streaming sources with the idea that you could democratize operational data in a way that no one's really done before. And that no-code way works with Spark streaming via Delta tables or your favorite flavor of Kafka. And this really helps our customers to add event-driven architectures to their existing historical data stores and really enable true Lambda architectures where you have a combination of batch and streaming inputs. And Kyvos has a strong partnership with Databricks because we leverage Delta tables for actual file level queries within cloud object stores. And we also enable streaming updates via Delta tables as well. And we leverage job and interactive clusters for the pre-processing of our smart aggregate files, which I'll get to in a minute. And then a lot of people want a fully governed semantic layer, so we integrate with the Unity catalog to enable that. And we also support query push down into the SQL warehouse for row-level queries. Okay, so we talked a little bit about the problem that we're trying to solve. We talked a little bit about what we are, and now let's talk about why we think our technology is a lot better than legacy alternatives. And really underlying our secret sauce is a revolutionary process that we call smart aggregation. And what we've essentially done is created a file format that provides the ability for us to continuously pre-aggregate data without the historical constraints of combinatorial explosion. So basically, it's a more efficient way to pre-aggregate data. And then on top of that, we've also figured out a more efficient way to leverage pre-aggregated data. And as a part of that, this technology is theoretically thousands of times faster than other alternatives, but it's enabled us to actually deploy it as a disk-based solution because it's so performant. And the reason why that's important is that we can still be disk-based and still be hundreds of times faster than complementary in-memory solutions, which enables our nodes to have a higher data density and really a lower cost. And what that pragmatically means is that a 5 to 20 query node system can easily outperform alternative systems with hundreds, if not thousands, of nodes, providing a better solution at a significantly lower total cost of ownership, and really an unparalleled user experience, because with Kyvos, all of your queries appear to be instantaneous to the end user. And it also, having a more efficient architecture really enables us to scale up very easily, even until the trillion row source data set range. Okay, and smart aggregates are not just another copy of your data. So with this, Kyvos doesn't need to be part of an ETL pipeline if you don't want it to be, because what Kyvos does is we actually read data directly from the source system, and then we build our aggregate files on our back end without needing another tool in the process. And it's a very flexible design. So the idea is we only work with new data. So unless your data has been changed or new data is being added, your aggregates stay in place and don't require constant reprocessing. And the way we work is very similar to a change data capture process, with the major difference being that with Kyvos, you don't need to include an expensive extra data integration product to make this work. It's really like getting change data capture for free. And then another thing that we consciously did as a part of our architecture is not to share workloads. And unlike a lot of other legacy technologies, our queries are never impacted by our simultaneous loads. And that's really important in a Kyvos environment, because you can load essentially continuously. Another cool thing about the smart aggregation process is there's no trade-off between precision and performance. So you really get consistent query performance regardless of the granularity of your data. So there's no curiosity tax associated with us. And we're not only fast on the query side, we're actually fast on the data load side. So this is an actual customer use case of ours where we loaded 21 billion rows in less than an hour on a fairly small Spark cluster of just 21 nodes. And at the end of the day, consistent with our overall goal, we're trying to provide faster loads and queries, because doing so, again, in a cloud environment really lowers your cloud consumption costs. Another cool thing about smart aggregates is that they can live alongside raw row-level data directly from the source system. So again, you get this best of both worlds implementation where you can leverage the aggregates where appropriate to accelerate trend analysis and row-level data for audit purposes. And in Kyvos, even though we have lots of files on the back end, they're presented logically as a single object. So that significantly simplifies the design process, the development process, the deployment, the enhancement, and the population of our data store. And on the query side, it also means you're only querying a single object, so there's no need for joins. And one of the paradoxical things about query time joins is that a lot of the other alternatives, for pre-aggregation, actually force you to make a lot of data model changes to enhance the performance, but you create so many objects as a part of that, you actually rob part of your performance by forcing those objects back together via query time joins on the back end. Okay, so let's compare smart aggregation versus some other query acceleration techniques. And I'm going to start off with the aggregate table approach because it's probably the one that we most commonly encounter. And the way aggregate tables work is if you have a star schema, that schema is going to have certain levels of granularity built into it. So, for example, if we take a retail store's sales geography, it might contain the following hierarchical levels. So, starting at the region level, a single region might have multiple countries. A country may have multiple states. And then there are multiple counties within states, multiple cities within counties, multiple postal codes within a city, and then there might be multiple geographic coordinates tied to individual postal codes. So each level of this hierarchy would require its own aggregate tables to deploy it. So we already have seven aggregate tables that you would need to build to power this schema so far. However, people tend to group things by time because it adds a lot of meaning to your analysis. So there are 6 common time grouping levels that people usually implement. However, there could be more. So most people would at least implement yearly analyses, quarterly analyses, monthly analyses, weekly analyses, daily analyses, and maybe even the hour, down to the hour. So if you had to group your data by each one of these time periods as part of an aggregate table mentality, you'd have to multiply the number of time periods you were trying to group the data by the other levels of the hierarchy. So with this very simple star schema, we're really talking about 42 tables have to be built just to accelerate it. And if you don't do this on the front end, on the back end, you have to do it on the front end during query time, which would be very costly from a performance perspective. But in the real world, people rarely can power their analysis of the entire enterprise just with a single star schema. So like in this case, retail stores, if you have a sale, they have to be satisfied by store inventory, so you have something to sell. So if they had the same hierarchical levels and were grouped by the same time periods, you'd be adding another 42 aggregate tables to power that star schema. And then most modern retailers don't have just the brick and mortar channel of revenue. They also have an e-commerce site. So you've got to have another schema that takes care of e-commerce sales. And e-commerce retail actually has a different fulfillment method associated as a part of that. So you have to track orders related to those sales as well as shipments. And each time you add another star schema as part of your multi-fact schema, you continue to deploy at least another 42 tables. And then to bring it all back together, marketing drives sales in both the brick and mortar channel as well as the e-commerce channel, so you've got to add another 42 tables to deploy in this matter. And even with this very simple schema, it requires a total of 252 aggregate tables to accelerate it. And guys, that's a lot of tables and a lot of work. So if we compare the aggregate table approach to smart aggregation, from a schema complexity standpoint, 252 tables is very complex to design, very complex to deploy, maintain, populate, and query. Whereas with Kyvos, we're always building a single object, right? So it's simpler to deploy and design as well as to query. When you think about the number of tables, a lot of precision is going to be required on both the front end and the back end there. Whereas in the case of Kyvos, it's just an easier way to get to that same objective, because Kyvos is already going to build those grouping levels automatically as you deploy that one object. And then if you're trying to enable self-service, which is a major initiative at most of our customers, that level of complexity really limits self-service, because if you ask a non-technical business user to join 2 tables together, that's a pretty big ask. If you ask them to join 5 tables or more together, that's usually a non-starter. So it's a significant deterrent to self-service, whereas in the case of smart aggregation, if you're asking them just to connect to one object and then just explore it as a part of their analyses, that really facilitates self-service. And then if you think about things from a total cost of ownership perspective, building all those aggregate tables is not going to be free. And it's not going to be free whether or not you use your own FTEs or whether you're using external consultants, right? There will be fees for that. And then on top of that, there are just so many things to build that an implementation timeline using that methodology is literally a quarters to year-long runway, whereas within Kyvos, again, it all comes back to just designing and building one object. You're looking at more along the lines of weeks to months for an implementation. Okay, so just to bring this home with an actual customer example, before Kyvos, this customer had over 200 aggregate tables. But even with all those aggregate tables, they were struggling to analyze just 30 days worth of data for a single customer. And they have hundreds of customers. They had a query SLA that was pretty lenient at 30 seconds, but they couldn't even approach it with the average query execution time over 60 seconds. And it was really just creating a horrible user experience for consumers of their system. And then in addition to that, they were basically failing in their analytic project. And then after Kyvos, they were able to change the deployment model from 200 aggregate tables to just one object. And by doing so, they went from being able to analyze, or barely being able to analyze one customer's data for 1 month, to being able to analyze all of their customers' data across all 61 historical months worth of data. And even if 25 concurrent queries were running at the same time, the execution time of each individual question or each individual query was well under 1 second. If we compare smart aggregation to another popular technique, massively parallel processing, or MPP, MPP takes a long-running process and just splits it up into chunks, and then the chunks are spread across multiple nodes in a cluster, and each node operates on an individual chunk's worth of work in parallel with the others. And then as a final processing step, they aggregate all the totals back together. Now, MPP works best when you have regular data, and with that assumption, if you have very regular data, the more nodes you have, basically the faster you can process a query. And it's called massive because you can easily have hundreds, if not thousands, of nodes processing any given workload. Okay, so when you think about this from a node perspective, if you have hundreds of nodes required to process a query, you're going to have to rent those nodes during that query processing, and that's not cheap. And then on top of that, if you compare that with smart aggregation, Because our nodes are so much more data dense, and we just figured out a better way to process queries, we can do more work with 5 to 20 nodes than an MPP system can do with hundreds or thousands. From a query latency perspective, one of the challenges of MPP is that there's a lot of data movement at query time because you actually have to co-locate individual columns or tables on specific nodes so that you can join them together at query time. Well, we don't do query time joins, so there's no latency overhead for data movement at query time. And another big challenge with a massively parallel processing is that data movement that happens on the system really makes it hard to have high query concurrency, because what happens is as you run multiple queries simultaneously on a single node, that node really gets pulled into 2 different directions and really has a lot of I/O contention. And the problem actually gets exacerbated with each individual query that you add to the system. So the problem gets worse over time because as you add more queries to the system slows down, and then more queries wait, and then more queries run concurrently. Whereas in the case of smart aggregation, first off, it's hard to have a concurrent query because our query throughput is so fast. But because we don't have to do that data movement, we can easily handle thousands of concurrent users and hundreds of concurrent queries. And all those nodes, running them is not free, so MPP architectures have a high cloud cost, whereas smart aggregation, you're only renting just a few nodes, so we have a very low one. Okay, another customer example. Before Kyvos, this customer, who was a large telecommunications customer, had over 1,000 nodes in an MPP system. And while they could process the workload, I wouldn't exactly call it interactive, because a single query execution took over 1 hour, and if you tried to make it concurrent, it was much worse. And again, other than batch process or like batch reporting, it just wasn't serving the real needs of the business. They were able to implement Kyvos, and they were able to replace it with the world's largest Kyvos implementation, which was 30 query nodes. And even with 25 concurrent queries, the average query execution time was less than 2 seconds against that massive data set. Another popular technique is in-memory columnar storage. Columnar storage is pretty novel in the fact that it doesn't really operate with tables. So it focuses on individual columns during query processing, and it really concerns itself with queries contained in the select clause, the where clause, and the join clause. And then most people further accelerate the process by using RAM as the storage medium, because RAM is just inherently faster than other storage tiers. Okay, so now the thing about columnar storage is that it does make your system RAM bound by definition. And you're going to need high RAM nodes, and they are very much more expensive as you try to scale upwards. And well, smart aggregation, like, we're disk bound, we're not RAM bound. So as a part of that, we require much fewer nodes in our query cluster, and because our data density is so high by using disk, they're far more less expensive nodes. And those expensive nodes cost more every month, whereas ours are much less. And if you think about this from a TCO perspective, while MPP architectures still provide query performance alternatives, they're not really solving any kind of model complexity issue. You're still dealing with like raw source tables that have to be joined together, and even if they're in a dimensional model. And so there's still a lot of objects to deploy in an MPP system. Whereas again, with smart aggregation, you're still dealing with one object, and you're still dealing with a very short implementation timeline to get to production, as well as to ease consumption. Okay, another customer story. we had a customer using the market-leading Columnar database. It's a very popular system. I think they're having a convention somewhere else. As a part of that, they were working with 20 billion rows worth of data, and they just never could get queries to perform in that system. The project was literally failing as far as the deployment, and they had brought in very expensive third-party tuning experts in an attempt to try to solve this inherent performance problem with their Columnar database. Unfortunately, after 6 months, they had not made significant progress, so they contacted us. So, but before that, their single query execution time was over 60 seconds, and that was undesirable for them. After Kyvos, we implemented 12 query nodes, as a part of that, we were able to generate 25 concurrent queries against their entire enterprise data set without filters even, with an average query execution time of less than 1 second. Okay, so the last legacy acceleration technique, I'm going to talk about our legacy cubes. So the idea behind cubes was to pre-aggregate every combination of unique data value and an attribute and measure, and then you would organize them into a cube. And then the cubes were stored in RAM again for ultra high performance query execution. Now the thing about legacy cube technologies is they operate on a single node. And even if you have a super node, that really limits the amount of resources that you have available. Whereas with smart aggregation, we have a fully distributed architecture that we actually have multiple subclusters underneath. So we have a subcluster for data loads and a subcluster for queries. Legacy cubes weren't known for their flexibility. So if they ever had a schema change, there were just lots of triggering events that would constantly require legacy MOLAP customers to reload cubes. Kyvos works with new data or changed data. So we have an ultra low latency incremental load process, and we also enable continuous streaming ingestion. So you're not going to constantly need to rebuild your aggregates over time. Then another challenge was legacy cubes operated under a mixed workload. So what that really meant was that data was unavailable for query during load periods. Whereas in Kyvos, data is always available for query as long as the cluster is live, because it is an elastic environment. If it's not live, it'll wake up. And loads literally have zero impact on query performance. In fact, your users will not even know that they occur. And then the other thing is about that single node architecture. It impacted legacy MOLAP users in multiple ways. So you actually had to design more objects to satisfy a given use case because you were really limited by the amount of RAM buffers you could work with. And just like in the case of aggregate tables, that was a complicated process. And then with Kyvos, we essentially have a limitless scalability because of our data densities and the overall smart aggregation process. And again, you can still design a single object regardless of data scale to satisfy your use case. And when you think about legacy cubes from a TCO perspective, they even had a higher TCO than potentially even an aggregate table because they required very expensive, very hard to find resources that really focused on multidimensional analyses. And with Kyvos feels like a relational database. So you can use commonly available skills that are generally lower cost. Okay, so just to give a customer reference, before Kyvos, this particular customer was maintaining 15 MOLAP cubes in a specialized BI tool, and then That limited their analyses to 1 year of data, and that was suboptimal. They really needed to analyze a much longer time period. And then on top of that, the process of building the aggregates in a legacy MOLAP cube is a very time-consuming one. So it actually took them 2 days to load data. So they were looking at day +3 reporting. So after Kyvos, they had one object to query. They can now analyze 2.5 years of data, which was their goal, and they could easily analyze more if they had a different goal. And now they actually do hourly data loads, and hopefully in the future we'll get them to real time. And again, with sub-second query, concurrent query execution. Okay, we'll give you a little preview about how we do it really quickly. If you'd like to have a more extensive conversation about our architecture as well as the semantic layer itself, we'd be happy to have you stop by our booth. So this is a high-level architecture of how Kyvos works. So Kyvos is the beautiful orange semantic layer in the center, and a semantic layer serves answers to calling applications. And for us, that's generally a BI tool or maybe a data science tool, but it could even be a mobile application or a website. It's really anything that really needs analytic content for end users or for applications to consume. And as long as they communicate via SQL, MDX, DAX, or one of multiple APIs, they can actually consume data from Kyvos. And how Kyvos works is that we actually live alongside data sources like Delta Lakes, data warehouses, whether they're on-premise or in the cloud, or query engines like Presto, for example, or even consuming content directly from a cloud object store at a file level. All of those things are possible. And then we actually store our aggregate files within the cloud itself. But you can see we subdivide our architecture into BI servers, which just handle incoming queries and help us with query concurrency because they can horizontally distribute the query load. Our compute engine, where we actually build our smart aggregates, actually is primarily done by Databricks. And then we also have a query engine subcluster. And then over on this side here, we have an intelligent cache that spans all the tiers of the semantic layer. And the idea of the intelligent cache is that we put your data on whatever storage tier really makes the most sense from a price to performance perspective. Okay, so I'll just move on and very quickly show you a quick video that depicts our semantic layer and how consistent the schema is deployed across platforms. And I mentioned before that we organize a schema into nested folders, and the idea is that anyone can instantly identify what data to go after. So in this case, if you wanted to find out where customer data is, you'd just go into the customer folder. But remember this format as we advance to the actual consumers of the BI tools. So in the BI tools, whoops, let's do that again. The schema remains consistent. So as you can see, all they do is they connect to Kyvos and they inherit that schema and they retain that consistent view of your data and consistent data definitions without having to recreate it in the BI tool and then eventually have your schemas start to converge because, okay, yeah. Then, so if Joe builds one version of a measure in one tool and Jill builds another in another, then 2 weeks later you don't have two different versions of the truth. And that's what our semantic layer looks like. And just to give you a performance baseline against a 6 billion row industry standard star schema performance benchmark data model, which we use for performance testing because it's really the fairest comparison of performance. You can see that even against 6 billion rows, one query is less than 1/4 of a second, and even 100 concurrent ones is less than 0.8 of a second. So if you want to know more, come visit us at our booth. Thank you.